Welcome all participants of the first virtual European Conference on Fracture. My name is Lutsenko and I am the PhD student of the Department of Mathematics, Physics and Information Technologies of the Odessa Mechnikov National University. My supervisor is Natalia Vaysfel'd, Doctor of Science, Professor of the Department of Mathematics, Physics and Information Technologies of the Odessa Mechnikov National University. We bring to your attention the research of the dynamic thermoelasticity problem for the hollow finite cylinder with a cut along the generatrix. We will start from the problem statement. Then we will introduce special notation which allow us to simplify the solving of the problem. After this, we show how to reduce original three-dimensional equation system to one-dimensional equation system by the integral transforms method. Then we show how to solve vector boundary problem by green matrices method. And the final step is to obtain the exact solution of the original problem. We consider the steady-state problem of incoherent thermoelasticity for a finite hollow elastic cylinder, which occupies the region in a cylindrical coordinate system R, Phi, Z. On the inner and outer cylindrical surface, ideal contact conditions are given, Formula 1. Without limiting the generality of reasoning, we consider a dynamic normal load applying at the upper face of the cylinder, and there are no tangential stress there, Formula 2. The bottom face of the cylinder is fixed, Formula 3. The cylinder is under steady-state oscillations, Formula 4. It is required to determine the thermal wave field of the cylinder under steady-state oscillations. Such problem in the static statement was solved earlier. We assume that the temperature field is already known. We note that the problem formulated in this way is equivalent to solving a similar boundary value problem for the dynamic and homogeneous Lamé equations with volume forces of a special form. We introduce the notation for the displacements in the cylindrical coordinate system, Formula 5. Considering this notation, the dynamic thermoelasticity equations have the form, Formula 6, where G, shear modulus, mu, the coefficient of the Poisson, alpha T, the coefficient of the linear thermal expansion, T, temperature field, delta, Laplace operator in the cylindrical coordinates. Partial derivative with respect to R is denoted as apostrophe. Partial derivative with respect to T is denoted as dot. Partial derivative with respect to Z is denoted as comma. We introduce the special notation for functions Z and Z with star, Formula 7, taking into account the ratios 4 and 7, and after some operations applied, the equation 6 takes the form, Formula 8. U and V are expressed through Z and Z with star, like Formula 9. To reduce equations 8 to two-dimensional form, we apply the integral transformation with respect to phi, with the assumption that phi 0 is equal to 0. The direct integral transformation have form, Formula 10, with inverse transformation, Formula 11. This transform allows to satisfy the next conditions, Formula 12. We want to use dimensionless coordinates ρ and zeta, so we introduce notation, Formula 13. After applying of the integral transform 10 and making the substitution 13, we get two-dimensional equations, Formula 14. Here and everywhere further, partial derivative with respect to ρ is denoted as apostrophe, partial derivative with respect to zeta is denoted as comma. To reduce equations 14 to the one-dimensional form, we apply the integral transformation with respect to ρ. The direct integral transform have form, Formula 15. Phi mu is naming function, J mu is Bessel function. Eigenvalues mu k are positive roots of the transcendental equation, Formula 16, and the inverse transform have form, Formula 17. Function phi n satisfies Bessel's equation, Formula 18. By applying the integral transform 15, we satisfy the next boundary conditions, formula 19. Thus, after integral transform 15 applied, we got the one-dimensional equation, formula 20. The solution of the obtained one-dimensional differential equations will be built so that the boundary conditions too are satisfied. To write boundary conditions true in the notation 7, we consider similar combination for the tangential stress tau ZR and tau ZP, formula 21. According to the Hooke's law in the cylindrical coordinate system and after integral transforms 10 and 15, we got the next boundary conditions, formula 22, and homogeneous boundary value problem for the function Zn with star. We introduce the next functions as unknowns of the system 20, formula 24. Thus, we write down the system 20 as vector boundary problem, formula 25, where vectors E with F and matrix PK have form, formula 26. The last part of vector boundary problem is boundary conditions, so we write down the boundary functional in form, formula 27, where matrices A and B are, formula 28, and join boundary conditions to equation 25, formula 29. Vector boundary problem 25-29 was solved by the green matrix method. To build green matrix G, we need both fundamental matrix F and fundamental basis matrix C. Thus, first of all, we need to find eigenvalues and attach matrix of Pk. Eigenvalues of Pk are plus minus lambda 1 and plus minus lambda 2, where lambda 1 and lambda 2 have form, formula 31, and attach matrix of Pk have form, formula 30. After applying of Fourier transform to equation 25 and substitution of Pk attach matrix, we got the fundamental matrix, formula 33. To find fundamental basis matrix C, we need to solve the next boundary problem, formula 34. Solution of the equation from 34 have known form, and after residue theorem applied, we got the solution for it, formula 35. By direct substitution, we can verify that the solution of boundary problem 34 have form, formula 36. Thus, all parts of the green matrix was found, and the green matrix have form, formula 37. And the final solution of the vector boundary problem 25-29 is a vector, formula 38. Thus, the displacement transformations VNK, ZNK, and ZNK with star were found. The final step of the problem solving is to find the displacements UNK and VNK from system 9. We introduce the notation, formula 39, and considering this notation, system 9 can be written down in form formula 4. Further, to satisfy boundary conditions 1, we apply different sequences of integral transformations to equations of system 4T. To obtain U and K with star, we use the next integral transformations, formula 41. Inverse transforms have the same series expansion form as we considered previously, but with another eigenfunctions and eigenvalues. To obtain V and K with star, we use the next integral transformation, formula 42. Thus, the displacement transformations U and K with star, V and K with star, W and K are found. By inverse transformations formulas, we find the originals, and by formulas 5 and 39, we find the displacement. Now we can discuss current result in future steps. First of all, the problem solution was derived, which allowed to determine cylinders' non-zero displacements and stresses. The potential next steps are complicating of the problem by boundary condition change and by adding a crack or inclusion inside cylinder. The numerical experiment is still in progress. Main goal of this experiment is to find eigenfrequencies of the cylinder. It will give us an opportunity to detect the existence of the cracks inside cylinder. Of course, if the corresponding boundary problem with the graph will be solved. The result will be shown in paper. Thank you for attention.